I'll just wait for like 10 seconds more for everyone else to join back, and then we can start off. So yeah, okay. So starting with thermal simulation, the agenda for this session is mainly going to be the introduction on the why thermal simulation is important and how thermal simulation help in guiding engineering decisions. Then we'll be defining the material properties. The material property definition for the thermal simulation are a little different as compared to those of a structural simulation. Then we'll be defining the thermal initial conditions as well. We'll be setting up a thermal scenario and we'll be running an example on a thermal simulation. That is, we'll be running a simulation for a cell model. So we have a cell model which we can take as an input, and on that we'll be working over the thermal simulation aspects. So starting with what exactly is thermal simulation? So thermal response of a system, once you give it any thermal loads with time, you'll have a thermal response, that is thermal stresses that are generated or the change in temperature that the given product has. So those type of details are encountered using thermal simulation. Now, where is it used in industries? It's used in the automotive sector. So in automotive sector, mainly in the engine compartment, wherein the cooling and the heating of the gases happens. Then we have also in the disc brakes of automotive vehicles, wherein the discs, once you brake a vehicle, you have the discs that generate heat, and those simulations can be done. In a power industry, for power industries, you have the gas industry, nuclear, solar industries. You have a lot of heat exchangers that are present there. In those kind of industries, you can use your thermal simulations. Then even in your basic smartphones that you have, so the electronics which are part of it, so the system cooling for these electronics, you could do a thermal simulation for that. And for industries, it's basically the heat exchangers, the valves, which we have, the flow limiters, and all of those components. For an aerospace industry, it's very important. So for any space probe that is going towards a different interstellar object, then for that, the space probes have a heat shield, so the heat shield simulations can be done. Then you have the basic engine itself for an aircraft. So you could do the thermal simulations for those itself. Now, the type of simulations that Abacus can handle is thermal electric type of simulations, thermal mechanical simulations, then thermal electromagnetic. You also have piezoelectric and thermal mechanical simulations. So these are a few types of simulations that you could handle on the Abacus solver. And there's a lot more to it, obviously, but a few of them are these which are mentioned here. So starting with thermal simulation itself, so it basically investigates the distribution of temperature over a long-term thermal response and how these thermal loads act on the given component itself. So if you have a component that may be subjected to a constant temperature, or you can either subject it to specific heating and cooling areas. So if you want to point out to a particular region and heat it or cool it, you could specify that too while doing a thermal simulation. And over time, the various thermal conditions create a constant distribution across throughout the product itself. So you'll have a simulation which looks something like this in the image which is shown there. So over a period of time, once you run this simulation, the temperature plot is almost like the same for a few of these regions. So when do we actually require a thermal simulation is something when we want to generate a thermal field. That is, we want to analyze the thermal behavior for a solid or for a fluid. So that's when we actually go in for a thermal simulation. And the different types of heat transfer that occur are basically three types. You have conduction, convection, and radiation. So a little bit more about it on the further slides. But these are the three types of heat transfers that we have basically. So conduction is your basic one. Then we have convection of the heat transfer through a moving fluid, and radiation is using the electromagnetic waves that are emitted through these components. And one more thing that we have to note in a thermal analysis is that there are two types of heat transfer analysis that you could do. So it could be either a steady state heat transfer analysis, or it could be a transient heat transfer analysis. So a steady state heat transfer analysis is something which does not depend, it's time independent and does not have the internal energy variable. So basically, the internal energy variable in a heat transfer equation is not present in a steady state heat transfer. But the same thing is present in a transient heat transfer analysis. So the internal energy term, which was neglected in the steady state, is present in the transient heat transfer analysis. If you can see the equation which is mentioned there, you have the material property plus the temperature dependence uh, of the property too. And the transient analysis, if you do it for a long span of time instead of for a given, the results are similar to that of a steady state heat transfer analysis itself. And the options or the commands that you'll be using in order to have these simulations generated are the ones in the last graphic that are shown there. So if you use the first option there, it will help you in generating a steady state heat transfer analysis step. If you use the second one, it will help you in generating a transient heat transfer analysis step. Now, a little bit more we'll see about what is conduction, convection, and radiation. So conduction is basically the heat transfer through the molecular interaction in a given solid. And the given formula is the conduction formula is the one, so Q is equal to minus K d theta by dx, wherein the Q could be either positive or negative based on the convention that is followed. And the thermal conductivity value, which is K, is there's a unit for it, and it basically measures how easy it is for heat to flow through these materials. So this was about the conduction properties. Mainly through the material molecular interaction that happens, the conduction happens. Then convection is something where the transfer of thermal energy happens once when a surface is moving through a fluid. So if you can see the example which is shown here, we have an example for a submarine. So the submarine is something that is moving through the fluid. So there's a heat transfer that happens between them. Now the equation for heat transfer for a convection is you have the formula on the screen. So it's Q is equal to heat flux is equal to minus h d theta, that is change in temperature. And the value could be negative or positive based on the type of behavior you are or the convention you're following. And one more thing to note is the convective heat transfer coefficient, which is there. It mainly depends on the flow materials like density and viscosity and the flow behavior. So if the flow behavior is either laminar, turbulent, or compressible or incompressible, then that will also be accounted for when you're working on a convection type of a heat transfer. Okay, so next we'll be moving on to radiation. So radiation is basically the transfer of thermal energy through a media by or vacuum by electromagnetic waves. So in terms, if you're doing a radiation type of a heat transfer, you'll also have to define the emissivity values, and the equation which is used to calculate these are mentioned in the screen itself. That is Q is equal to minus sigma emissivity into T1 power 4 minus T2 power 4. So you have your Stephen-Boltzmann constant, which is sigma, and that's how you'll be calculating your heat flux through the radiation process. So now that we have covered the basic types of heat transfer steps and the heat transfer, how it happens between solids, we can go a little bit more and understand how to define the material properties. So before we enter the material properties, we need to know that since the meshing will remain the same irrespective if it's a thermal heat transfer or a structural heat transfer, a structural analysis or a thermal analysis. So the meshing part will remain the same as we did in the first session. So you'll be defining your mesh exactly how you did it. It's only that the material properties need to be a little bit different right now. So instead of defining the elasticity and plasticity values, you will have to define the conductivity, the specific heat, and the density values for the components. So for a steady state heat transfer, all you'll have to define is the conductivity values. But for a transient heat analysis, you will also have to define the density and the specific heat transfer values too. So this is one thing that we have to note based on these steps which we use. We have to define these properties. Else the simulation won't go forward and you'll encounter errors towards the end of the simulation. Now, how do we create a heat transfer step? So I'll take you through the process of creating a heat transfer step itself. So once you open your structural model creation, the mechanical scenario creation app, so like we had earlier selected the structural component, here we'll have to select the thermal component since we are trying to achieve a thermal simulation here. Then we have either the static state heat transfer step that we'll select or transient heat transfer analysis step based on the type of requirement or the type of simulation we are trying to achieve. So if it's a steady state heat transfer, then in that case, the first window on the right side will pop up, wherein you'll have to specify your total time, your time increment, minimum time increment, maximum time increment, and the maximum number of increments. Else, if it's a transient heat transfer step, then you'll have to define your initial time increment, maximum and minimum time increments, and you'll also have to define the temperature change that occurs per increment and the maximum temperature change rate for steady state. So these are a few properties that you will have to define based on the type of simulation that you're trying to achieve. And the next part is basically the thermal and initial conditions which we have. So thermal conditions are basically used to assign boundary conditions. So it's the boundary conditions which you apply in regions of a part. So these conditions may result something like if this particular product is a part of a different component, or if it's a part of a greater assembly, or the interaction of the component with the environment itself. So for example, if you're giving a constant temperature to a given component, now maybe it's just an interaction with the environment, or this particular component has a constant temperature when it is working in sync in an assembly. And the most basic initial condition that you'll have to define, the thermal condition, is the temperature. So that is the most basic type of thermal conditions that you define. So the constant temperature is something that you apply when your given component is a part of a much larger assembly or its interaction with the environment itself. And one more thing we can do is the selected phase or the selected component on which this temperature value is assigned. It could either be a constant value, so you can give in like maybe 100 degrees Celsius or anything like that. Maybe it may be a constant value, or you can give an input of an amplitude curve, and this could be something that varies with respect to time. So the user has that option. If they want to vary the temperature with respect to time, they can give a amplitude curve as an input. Else they can just give in a constant temperature that is to be followed throughout. In the example which you see in the screen is basically the outer surface is given a fixed heat, a fixed temperature is maintained to the outer surface of the component. So the next thermal condition that we have is heat flux. So heat flux basically represents a region that is subjected to external heating or cooling. Now, a positive heat flux means that heat is flowing into the model, and a negative heat flux indicates that heat is flowing out of the model. So, based on the value which you given in your heat flux window, so if it's a positive one, then it's heat flowing into the system, and if it's a negative one, it's heat flowing out of the system. Now, again, in this case, you could either give a constant value or an input of an amplitude curve. So the user has that option of giving an input based on their requirement. In the example which you see here, the heat flux is towards the end surface of the pipe in order to simulate the heat flowing into the end of the pipe from the adjacent structure. So you can give in a heat flux input like this. Now the next one which we have is film condition. So film condition is basically used to simulate the heat transfer between a part and its surroundings through convection. So while you're defining a film condition, basically you will have to define your transmission surface, the temperature of the surrounding fluid, and the film coefficient. So these are a few things that you will have to define, and the formula that it uses in order to calculate the film condition is Q is equal to H into T surroundings minus T surface. In the example which you see here, the inner surface of the given pipe is given a film condition type of a thermal condition, wherein the heat transfer through the pipe can be simulated. And there's further a lot more types of thermal conditions than one could define. So you have volumetric heat source. So for example, if you have a component that is generating internal heat, you can define the value for it in volumetric heat source kind of a thermal condition. Then you have radiation to ambient. So for example, if you have a component through which radiation is occurring, then in that case, you can define the radiation, but you'll also have to define the emissivity value. And approximate cavity radiation is something that we won't be discussing in this particular session, but what it means is basically the radiation between a surface and a non-reflecting cavity in which it is enclosed. So all you'll have to define is the emissivity value and the surface of the body that is taken as an input. And coming on to the final one, which is initial temperature. So if you're trying to achieve a transient type of a heat transfer, in that case, you'll have to define your initial temperature. But in a steady state kind of a heat transfer, you do not need to define your initial temperature of the component. It's only for transient heat transfer analysis that you'll be defining it for. And it could be defined for either a point, a line, or a surface based on how your model is. So you can define the initial temperature for them. Similar to the structural interaction which we had, that we do for structural simulation, that is load being transferred among the components on which the load is acting. In the similar way, so thermal contact is something that we need to establish in order for a simulation to be much more accurate. So if there's a heat transfer and these two components are close to each other, there will be some heat transfer that occurs between them. So to do this, we have the thermal contact, which is to be established here. So if thermal component is defined, if not defined, then your temperature changes and heat flux won't be affecting the other component, and your simulation results won't be that much accurate as well. And the other things to note is higher the conductance value, the easier it is to transfer heat between the components. And if a conductance value of 0 is being defined, then it prevents any heat transfer between the components itself. So just like your structural interactions, we have to define thermal interactions too while doing a thermal simulation. The next thing what we have is the contact which we define. So in terms of structural, we saw that there is either a general contact that we could establish or a surface to surface base, that is contact pairs that we can select. So similar properties given here, but instead of a general contact, there's something called as contact property. So contact property is something that accounts for the heat transfer across the interface. So something on the similar lines for general contact, except this contact property is used in order to generate the contact among the surfaces. So you can use the other one or other option too, which is the surface-based contact, and you can select the mating surfaces, the main surface and the secondary surface. And this contact property is what it is based upon. And for both conduction and radiation properties, there is options for input that is to be provided. For radiation, if there's a radiation type of a heat transfer that is occurring, you will also have to give in the emissivity values therein too. And at the end, once you have given all of these material definitions, the properties, the solid sections, if you have defined all of them, towards the end, the type of simulation which you will be able to achieve will look something like this. So you'll have a temperature distribution throughout the part. So the temperature distribution throughout the part will look something like this, wherein the red region is where the temperature is higher, and the blue one is which is the minimum temperature. And the heat flux is basically a vector plot of the heat flow throughout the part. So this is how your simulation will look towards the end once you have finally simulated your models. So now that we have covered this, and on the basis of the structural simulation side, we'll try to set up a basic scenario. So I'll take you through a basic scenario setting up that is done for a thermal simulation. So you just need to have a look at it. So what we're trying to do here in this example, as you can see, is basically we have a metal plate, and it has all the edges named as A, B, C, D. And there's a point E at which the temperature is to be determined. So first we'll be doing a steady state heat transfer analysis, and in the second step we'll be doing a transient heat transfer analysis. So if you can see, we have a few initial conditions that are defined. That is the conductivity, which is the K value for the given material, which is 52 watt per meter degree Kelvin or degree Celsius. It's the same thing. And then you have a film coefficient value that we need to define, that is 750 watt per meter square degree Celsius. And we have a few boundary conditions, that is the temperature value along the face AB is to be maintained at 100 degrees Celsius. And the heat flux that is to be given along BA, that is 10. And since it's a positive value, it's heat flowing. Uh, since it's a positive value, it's free heat flowing into the system. So that will be the value along dA. And you have convection to ambient, which is the film condition, which we apply along BC and CD at 0 degrees Celsius. And the target solution, that is what we have to achieve, is at point E. The temperature at point E is what we're trying to achieve here. Now, how do we do that? So we start by creating a mesh. So you create a mesh for your given component. That is, either you can initialize it from the geometry, or you can give in your own mesh size and mesh sag values. Now, for this particular example, they have taken a sweep 3D mesh, which is one of the meshes that are present on the uh, the structural model creation app. So you can select that, you can give in your mesh properties. And once you have given that, then on side AB, okay, so one more thing you have to do is you have to create one point on which the temperature is to be measured. So you'll have to manually go and select that point on your geometry. And once you have created your mesh, and the next thing which you'll have to do is you'll have to create a transient step. So you'll have to change your model. You'll have to enter the model scenario creation app, mechanical scenario creation app, and then you can select the steady state transfer step, given the values for the time increment and the temperature values. And then you'll have to start by defining the temperature. So the first thing, as in the example, what they have done is that they have put a 100 degrees Celsius temperature along line BC, I think. Yeah, they've put it along line AB. So along line AB, they have put in a 100 degrees Celsius. They have initialized that temperature there. The next thing that they have done is they've given a heat flux along the face DA. So the heat flux value is 10 watt per meter square per degree Celsius or Kelvin. So once you define that, the other two things are basically the film condition. So you'll be defining all of these values, and you'll have to enter the film coefficient and reference temperature. So the basic objective is to achieve the temperature at that particular point E and to see how the temperature varies accordingly. So now that the point which you had created initially is the point you'll be selecting for the output. So for the output definition, you'll have to go and select that particular point, that is the temperature which is produced at that point. And towards the end, if you do a simulation of the plate, if you run it for a given amount of time, this is how your simulation will look like. So the temperature achieved at that particular point is about 18.3 degrees Celsius, which is about 291.45 Kelvin. So this is the methodology followed in order for the steady state heat transfer analysis. Now we'll take a look at the transient heat transfer analysis and see how the difference among them are. So it's the same example. The only change we'll be doing right now is we'll be using a transient heat transfer analysis instead of a steady state one. So if you open right now, as I told you while defining the materials, for a transient heat transfer analysis, you'll also have to define the density and the specific heat values apart from the conductivity. So for a steady state, it's only the conductivity value that will be required. But for a transient, you'll also have to define the density and the specific heat values. And the type of simulation analysis case, based on the type of simulation that you're trying to achieve, you could select that. Now, it could be either it could be a thermal structure wherein a thermal stress analysis could be done, or it could just be a thermal analysis wherein you're just trying to achieve the given temperature at that particular point and not bothered about the how the structural behavior changes for the component. So now you'll have to select the transient heat transfer step. So in transient heat transfer step, you'll have to give in the initial time increment, the minimum and maximum time increments, and you'll also have to define the maximum temperature per increment, the change that happens. And then you'll be creating a mesh. And since for a transient heat transfer analysis, you'll also have to define the initial temperature. So you go on by defining an initial temperature value of about 273.15 Kelvin. You'll define it as an initial temperature, and then you will try to replicate the process which you did for a static heat transfer analysis, wherein at phase BC you given a temperature value, at phase DA you given a heat flux and a film condition and all of that. So once you've done all of that and you finally simulate your model, you'll have a result which looks something like this. So the final model which you can see is something similar to your steady state heat transfer analysis itself. It's just that you will have number of steps that are produced and you could see as to how the temperature change occurs in each of these independent steps. So this is something which you could do with your transient heat transfer analysis. And the graph for the target temperature will look something like this, is what we have achieved. So now keeping all of this as a basis, we can actually do a thermal analysis, and we have a cell model on which we'll be creating a mesh, applying a material property, and then running a transient heat transfer analysis, and then seeing how the temperature of the cell varies is what we'll be trying to achieve now. So what we can do is we can quickly shift back to our platform. I'll just check if there's any doubts in this. Okay, there's no doubts. Yeah. So what we could do is we can go onto our platform, and right now I've shared you a file for the cell model too. So what you'll have to do is you'll have to download the cell model first. So you can go back to your 3D drive, and you can see there's a second component which is here, and you can download it. Yeah. So it's about a 4.8 MB file. So it might not take long. But let's give it a minute. You can download it and it will be saved in your downloads. So for the ones who want to see where the 3D drive came from, you'll have to just go onto your Compass, search for 3D drive. And the first file which is open there is simulation data. So you can just double click it and access the data from there. So make sure that you all are following, because towards the end we'll also have one of you share your screen and we'll try to replicate the process on your systems. So I'll give it a minute. You can download the file and then we can replicate the process of importing the given component. The ones who are able to access the component and their platform, can they just reply on the chat box by mentioning yes if they're able to do it? Without like, I'll need a head count as to how many are actually working on the simulation. Okay, that's good. There's quite a few of you who are working on it. Okay, so for the ones who have downloaded, I hope the file must have downloaded till now. So we'll replicate the process that we did initially. We'll go on to our plus icon and we'll do new content. So it's basically we are importing the file which we'll use import, I'm sorry. Yeah, we'll import the cell model which we had just created. So it needs to be a 3D XML file format. The source needs to be filed on your disk. You can select it from something else. But at this point, since the cell model is in our downloads, we'll just go and select the component. So like you can see, we have the cell model here. You can just select it, press on OK. And as I told you initially, just give in an initial duplicate string so that you don't get confused between what component is yours and you don't start working on a wrong component. So make sure that you give in some unique name or an initial. This will be added on to the initial part of your string itself. So I hope most of you are familiar right till now by how to import a component. So what you can do is you can just press OK once you've selected the file you want to import, and we'll let it open in the Innovia App Explorer. So I'll hold on a bit for the ones who are trying to import the model, and then I can tell you a little bit more about it. So okay, so coming back to the model, now that most of you have imported it, what you can do is you can open it. And once you open it, it'll enter into one of your modeling apps. So right now, if you see, this is how your cell looks like. You'll have an insulation cap, you'll have a center cell. The center cell is this particular component that is excluding your insulation cap, and the insulation cap is, so while manufacturing an EV cell, you put a cap on the top in order for the welding of the tabs can be done easily. So it's usually put there so that there's no short that happens between the cell while welding the component. Okay. So we'll come on to the standard. This is a design table basically. I'll just give you a brief about design table later on. And what you could do is we can just go through the simulation right now. So how many of you were able to import the model and have at this stage? Could you just answer in the chat box, the ones who are able are at this stage? Okay, so Praneeth was able to do it. Apart from him, who all were able to do it? Okay, no problem. Let's wait then. You can import it. I think we'll give it a minute or so, and then we can start with the rest of the process. Okay, not able to get the elementary. Okay, okay, I'll just show you one process which I think there might be an issue on your system or Diptesh. What you could do is just go onto the left side and the tree might just appear. I mean, usually it's hidden as well. You can just go and pin it back. But if that does not still happen, then let me know. I'll give you one more method that you can go. Oh, that's good. Anybody else who was facing the same issue like Diptesh was? They could answer in the chat box and I could help you with that too. So Vineet, were you able to import your model? Okay, good. Okay, so I hope everybody else was able to import their model too. So now we can start with the modeling process itself as to how the thermal simulation can be achieved. So we'll start by assigning a mesh to it. So for that, what we'll have to do is we'll have to change the app. And the app which we have to use is basically the structural model creation app, which we use for the initial previous session too. So you can just go onto your 3D compass, search for structural, and you'll automatically see that structural model creation app is shown here. So you can just open it and we let it load. Now there's again two options, either a standard or an empty. So what we'll do for this case is we'll go with an empty FEM because the standard one creates the representation on our tree, and I'll just take you through the other process too. So you can just select empty here. Now what you'll have to do, you can just press OK over here. Okay, just unwrite these. Yeah. So now that we have the global FEM representation that has been created, but the part has that are like the components which this particular assembly has have not been added to the global FEM. So for you to, in order to do that, what you have to do is you'll have to go into Setup in the action bar, and there is Contributing Shapes Manager. There are two ones. One is Contributing Finite Element Models, and one is Contributing Shapes Manager. So once you click on Contributing Shapes Manager, it will give you a window that looks something like this. So this is what is meshes of assembly. Okay. So you have SP cell model, SP center model, SP insulation cap cell. So if you click on it, it will be automatically linked to the global FEM. And on the similar way, the SP center cell too. So these two elements have been linked to the global FEM, and we can start by creating the mesh itself. So I'll tell you the process again. It's just Contributing Shapes Manager, and you can go and select which all components you require in order to generate the mesh. Press on OK. We'll just unhide these components. So just make sure you have done this step, that is, it's in Setup and Contributing Shapes Manager. So once you have done that, now we can shift the application. So right now it's on structural model creation, but we need to generate a mesh for these components. So in order to generate a mesh, we click on this drop down and there's a mesh option here. You can just click on mesh and it will enter into the mesh creation app right now. Okay, so this is how your different meshes are there. The mesh that we are going to assign for this component is a tetrahedral mesh, but you could also select any other of them. For tetrahedral, it works well, so I'll select tetrahedral mesh. I can just select on tetrahedral mesh, and now you can see I have to give in a support here. So in order for this component to have a mesh generated, I'll need to establish a support. And starting with our center cell, we'll define the support for the cell right now, and we can select part body from here. So you'll have to just go into SP center cell based on in your specification tree, and you can just maximize your 3D shape and then enter into the part body. That is, the part body is what we'll be using the support. And the mesh which we are going to define, make sure element order is on quadratic and not on linear. So the linear will generate the linear elements, while quadratic will generate your quadratic elements. So you can give in a mesh size of 2 mm again. So the mesh is again a very iterative process. So based on the type of simulations you're trying to achieve, and if there are any errors that are generated based on your current mesh selection, then in that case you'll have to iterate the process to generate a perfect mesh for your given component. For this case, we'll be using 2 mm and 0.4 mm sag. Now, since in our component it's quite a basic one and does not have a lot of stress concentration zones, we won't be selecting any local specification. We let it be the mesh size as 2 mm and the absolute sag to be 0.4 mm. And you can just click on mesh here. So what it does is it will generate a mesh for your cell. It is giving a warning signal. Okay, let's try and change the mesh sag value to maybe 0.2 mm. Let's see what happens. And now if we mesh it, it's still giving a warning signal. So there's no problem. I mean, if you just scroll through, it will be 505 mesh edges on volume boundary have been straightened. So it's just mentioning that there has been a change that is done in your mesh properties. So once you have your tetrahedral mesh, you can just click on mesh that you have done and you can click on OK. Now this mesh property has been created in your FEM representation in the tree. And since we selected meshes of assembly instead of assembly of meshes, the global FEM has the part FEM inside it. So if this was a complex assembly, then I had to every time to change or do any changes, I had to search the given mesh in the global FEM representation and then do the changes in it. So since it has two components, there shouldn't be an issue with it. The next thing that we have to do is we have to create a tetrahedron mesh for the cap which is present. That is the insulation cap, this particular component. So I hope everybody were able to do the mesh for the cell. I'll just repeat it, just repeat the process quickly. So you'll just have to go in tetrahedron mesh, and you'll have to go onto the maximize your cell component and go and select part body inside it. So once you do that, you will have your mesh generated for it. The mesh size will be 2 mm and the mesh sag will be 0.2 mm. Okay, so the next one is for the insulation cap. So we'll again replicate the same thing. We'll use tetrahedron mesh, but this time we'll select the part body for the insulation cap. So you can just select it, and you can see the selection in the tree in the geometry itself. And we'll let the mesh size and absolute sag be the same, and we'll mesh the component. And there are no errors that are generated, so you have the mesh that has been created for this. You can go for a finer mesh. Maybe I'll just go with 1 mm and you can mesh it. You can see the finer mesh has been created. So one thing you also need to notice, if you create a finer mesh, the amount of time it will take for your simulation will be a little longer than for a more not a dense mesh. So for a denser mesh, the time for simulation will also increase since the number of elements that it has to do the FEM for will also increase. Yeah. So now that we have done this, what we'll quickly do is we'll have somebody from you or from the audience who just we just see how their representation is done. Now, okay, so how about Praneeth? So Praneeth, were you able to create the mesh properties? If you have, can you just respond on the chat box? That will be helpful. If you haven't, then no problem. We'll do it on your system itself. There's no issue with it. Praneeth, you're there in the meeting, or okay? So what we can do is maybe Dr. Dheeraj, are you there on the call? Okay, so what I'll do is I'll randomly select one of you who is able to generate the simulation, and then we can be done with the mesh, right? Okay, Mihir has done. Okay, so what we can do is we can use Mihir's screen right now, and we'll try to generate the material properties on his screen. Okay, so I'll just make you the presenter, Mihir. You can present your screen.
Hello, Siddharth.
Oh, yes, sir.
Yeah, I think Professor Mahajan is busy in some other work. So
Oh, okay, no problem, no problem. I think since I have the rights, I can make them a presenter.
uh, uh, I can assign you if anyone wants to
Yeah, I just
increase your
assigned
screen.
Mihir Bagul, Mihir Mahindra, the presenter, right? So, Mihir, could you unmute yourself and present your
Okay.
screen?
Yes, sir, sure.
Yeah. Yeah, Mihir,
Is
you
my
can please see
screen
your screen.
visible, sir?
Oh, yes, your screen is visible.
Okay, sure.
Okay. So, okay, you have created the mesh, right? Right. Okay, so now what we can do is we can create the material properties as well. Okay, so I'll take you through these steps as to how to do that. So what you can do is you can change, so everybody can follows Mihir's screen itself and how he's replicating. So you see the mesh app, right? So how do you go back to your model using that drop down that you have? Go on to model, and now we'll be creating a material right now. Yeah. So you can go into setup maybe, okay, and you see the material option, right? So you can go into create a material. Okay. So you can give in a name, anything that you have. So you can give in a name. And can you just drop down the add domain option once? Yeah. So we have the simulation domain selected. For covering domain, you can make it 0, the one which is there. So we are not trying to create a covering material. It's just that we are trying to do a core material. Yeah, you can answer it that too. Now that we have named the cell material, could you also give in an initial or something, because it might get hard for you to find this. Just give in your name or anything like that, maybe it should be fine. Yeah. Okay. Click on OK. Okay. Yeah. So you have your behavior open, right? So you can close the screen on the right side, which you have open. Yeah. So now, in order to give a material property for a transient analysis, what we do is we'll have to give in the specific heat, conductivity, and density values. So what you'll have to do is just drop down Abacus Multiphysics, like just press on the arrow, and you have the thermal there, right? Thermal properties. So you can go into thermal and select conductivity. Yeah. Now, can you go back to conductivity once? Yeah. Now, the conductivity value that you'll have to enter is basically 90. So just given a value of 90. It will automatically give in the units. Okay, so the conductivity value. So this particular material is basically nickel for the battery sheet which we are using. And can you go into specific heat? Just below it, yeah, just select on it too. Yeah, so the specific heat value which we're going to give in is 500 joules per Kelvin degree kg. Okay, so now one more thing that we need to define is the density value. So can you go on to density once, just above? Yeah. And the density value that we're going to define is 8,900 kg per meter cube. Okay, so based on the materials that you have for a cell, you could use any other material too, but in our case, we are using nickel as the material properties. So you could just press OK, and we have the materials defined right now. Right. So what we'll do is we'll quickly apply this material. So what you can do is again go onto your material palette. The same option itself, just use the drop down menu there, just beside it. No, not that one. Just go on to setup back again, and there's a small arrow beside it, right? Yeah, yeah. Go on to material palette. And now what you'll have to do is you'll have to either go into in session or you can search for it. So we'll just go into, for the drop down, yes, you can use in session. And in there, no, just go back once. Yeah, so you have your material MB cell material, right? So you can just drag it and drop it onto your central cell component. Yeah, just the one above. Yeah, and just drop it there. And just click on the tick mark. Can you expand your cell component now? So you have the material already established. Now let's also create a solid section. Go on to properties here. Yeah, so you have solid section, right? So you can just click on solid section and select a support now. So the support you'll be selecting is part body. So you'll have to maximize the cell. No, not this is the cap. So you'll have to select in the cell. Yeah, so you can just select part body, and if you can see, the material will automatically come up. So you can just press OK. Okay, so now basically what we saw was we created a mesh, and then we assigned a material property to the component itself. So good job, Mihir. We'll actually now shift to somebody else and we'll replicate the same process for the insulation cap right now. Yeah, you can
Yes, sir.
stop
Thank
presenting
you.
your screen, Mihir. Yeah. Okay. So coming back, who else was able to do it? Yeah, I think Diptesh was also able to do it, right? Anybody else who wants to volunteer, they can raise their hands and you can show the process. I'll select Diptesh and yeah. Diptesh, I've made
Yes,
you as a
sir.
presenter. Could you share me your screen?
Yeah, sure, sir.
Yeah.
Okay.
Yeah,
Yeah,
we're
can
able to
you
see
see
it.
my screen?
Yeah, I'm able to see your screen. Okay, so now what we'll do is we'll create a material for your fell cap as well. So
Okay.
just go on to material. Okay, this is for the center cell, right? Now just go on to your material creation and let's create it for the cell. Yeah. And you can give in a name which you want, and you can just give in something as cap in the end. It's the insulation cap material which we're trying to give in. Okay, so the domains which we have is appearance, simulation, and you can unselect your covering material domain which you have. You can let this be selected, just the covering material, you can select it to 0, the number of materials. Yeah, just set it to 0 and press OK. Okay, so you have your behavior open now. So you'll have to go into structures, back is multiphysics, and then into thermal. Okay, so now we'll start by defining our conductivity value. So you can select conductivity. The value that you need to enter is 0.2. No, not there, in the thermal conductivity option, just below it. Yeah, right there. 0.2 is the value that you need to enter. Now that you have done this, you can go on to specific heat, just below conductivity. Yeah. And the specific heat value which you're going to assign is 1470. I'll just repeat, 1470 is the specific heat value. Yeah. And we also need to give in the density value. So you can just go on to density, which is above, just below Abacus multiphysics. Yeah, you can just select density, and the value that you need to feed in is 1070. Okay, so now that you have created this, you can just press on OK, and you can close this. And once more, you'll have to go onto the option for material with the drop down material palette. And from all, instead of all, you can select in session, the drop down which is on the top, right? Yeah, there.
It is taking some time.
Yeah, no problem. We'll wait.
Huh.
Drag it and drop it onto your cap component. So you have the material assigned, and you can click on the check mark here, and you can close this. And now we have to define a section property for it. So you'll have to enter properties on the action bar here, and go into solid section, the first one. Okay, so what you could do is you could just right click here on your screen. Yeah, just right click. No. Okay, no, not here. Just on the blank side, you have just right click there. Uh, okay, there's no option. Okay, no. Yeah, and do display icons and text. So this is, in this way you'll be able to know which command is what. So go into solid section and select a support. So the support for the cell is going to be part body. Just select your. There's no selection. Yeah, now you no, not here. The below one. Yeah. Okay. So you have your materials created and you have your solid section created now. So this is how we basically create a material, and we assign the solid section properties. Thank you, Ritesh. I'll take back the controls and I'll show it on my screen right now.
Sure,
Will
sir.
you stop
Thank you,
sharing?
sir.
No problem.
Yeah.
Yeah, just stop sharing the screen and then. Okay. Dharmendra, could you give me the, or maybe Lloyd, sir, could you give me the this thing, the presentation access?
Yes.
Yeah, could you give me the presentation access? I think I've lost it. Yeah,
Okay.
no, I haven't. Thank you.
You are already able to.
Yeah, I just got back the access here. So I'll just quickly replicate the process again for the ones who want to take a look at it. So I'll go into setup. Okay, I'll just change it back to model. I'll create a material right now. So my first material is going to be SP. So I'll create a cell material, and all I need is the simulation domain. I'll just press OK. So if you can see, there's a lot of materials present here. So if you try to locate your material, it might be a little bit hard. But in our case, we have the simulation domain that has opened up. So we go into structures, abacus, thermal, conductivity, specific heat. So we've just given a value for thermal conductivity, which is about 90. And we'll given a value for specific heat. The specific heat value is going to be 500. And also the density value. So the density value for nickel is about 8,900. And once you have defined this, we can just press on OK. I'll quickly create the other material too for the cell cap. So I have the material behavior open for it. All I have to do is go into structures, abacus, okay, thermal conductivity. So the conductivity for this component is going to be 0.2. The specific heat value is 1470. And the density value which we have is 1070. So once you have done this, you can just click on OK. And now we'll assign the given materials to each of these components. Go into in session. So I have these three materials. So the SP buckle material is from the previous session. So I have all of these materials open. So all I have to do is cell cap will go in here. I'll just click on OK. And similarly for cell material. So I have my materials defined. The next thing that I'm left to do is solid sections. So I'll just go on solid section, select a part body, the material property automatically comes in. Similarly, we'll do it for the cell too. Select a cell, the cell property comes in, the material property, and click on OK. Okay, so this is how we select the material properties for them. So what we'll do next is shift to our mechanical scenario creation app. So I hope all of you were able to follow up till here. So we'll enter mechanical scenario creation app. So this is where we'll have to select the step, so now you can see it's asking us for the analysis case. Now either we can select structural, thermal, or thermal structural. But in this case, we are doing a purely thermal type of a simulation. So we'll just select thermal here and we'll click on OK. So we have a thermal simulation. Now we have our assistant option that has popped up itself. So these are all the things that you'll have to define right now. Yeah. So what we can do right now is we can, I'll try to replicate it on somebody's system and then so that we can understand it and let's go better way. Okay. So yeah, were all of you able to follow up till this step? Okay. So, Okay, so okay, Akshay would be okay. So Akshay, I'll make you as a presenter, and then you can share us the screen, and we'll try to replicate the process on your system. I've made you as a presenter, Akshay. You can just share us your screen, and we can replicate the process on your
Yes, sir.
system.
1 second.
Sure.
Sir, it's not allowing me to present yet.
Okay.
I guess some net lag or something. I'll try again.
Sure. We'll just hold on.
Sir, it's not coming actually for me.
Okay. Okay. No problem. Uh, let me check. Okay. Dharmendra, are you there in the meeting? Are you able to lose control, Akshay?
I mean, the
You're
share
still not getting
option is not visible for me yet. So I guess some issue. I don't know.
okay. It's still grayed out on your screen.
Yeah, yeah.
Okay. Okay. Okay, no problem. Oh, okay. Let's see if there's somebody else whom I can make presenter. Okay. So Janki, just Janki. Okay. Could you unmute yourself, Janki Raman? Yeah. Hello, Janki. Okay, I'm not sure. Lloyd, so are you there on the call?
Yes, Siddharth.
Yeah. Oh, okay. Could you give me back the presentation rights? I think.
I'm not sure if I can do that.
Oh yeah, I got it. Yeah.
Can you present?
Yeah, yeah, I'm able to present now.
Right.
What I can do is maybe I'll just try to give it back to Akshay and let's see if it works now. Akshay, I'm just trying to give you the presenting rights again. Just check if you're able to get it now.
Yes, sir. I'll check it.
I've given you. Just check on your ones.
It's not yet update. I mean, it's not yet there.
Okay. 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 No problem. Then I'll do it on my screen itself, and let's see if further steps we can have done on some other screen.
Okay.
You can
Yeah.
present Akshay. Hello.
Oh yes.
Akshay can present. He's now a presenter.
Yeah. I think she's not getting the option on her
No, from
screen to
my side,
share.
I'm not able to see it yet. I guess
Actually,
my side there's an issue or something.
yeah, there might be some issue with net connection. From here, I have already assigned. You are a presenter. I can see.
Okay, so I don't know. It's not coming. I tried loading, but it's leaving the meeting. So I thought it's better to stay there.
Okay.
Okay, no problem then. Yeah. Okay, Dharmendra, could you give me back the presentation rights? Yeah, I'll just present
Yeah,
it on
yeah.
my screen.
I'm just assigning you. Yeah, you are a presenter now.
Sure, I'll just present my screen. Okay. So what we'll do first is we'll start with setting up the finite element model which we have created. So the thermal analysis case needs an FEM model in order for it to run. So we'll select the finite element model. And now you can see you have two representations here. The one which we'll be requiring is the one which has been created here. We just cross-check it, 3419. So this could be either some data from the system itself or the previous result. So we'll just select this 3419 and we can click on OK. And we have this check mark that appears here. That means your mesh property has been assigned with the thermal analysis case. The next thing what we have to do is we have to select a procedure. So in this case, since we are trying to achieve a transient heat transfer analysis, the two procedures you will have is either a steady state heat transfer analysis or a transient heat transfer analysis. So in our case, we are going to select a transient heat transfer analysis. And you can just give in the values as I feed in. So the step time is going to be 10 seconds. Yeah. And the maximum degree change per increment is going to be 1 degree or 1 Kelvin degree. So it's basically considering the Kelvin and the degrees. And the rest properties, you could keep it the same itself. So I'll just quickly repeat. You will have to just go into procedures. You will have to select transient heat transfer step. And in that, you will have to give your initial time increment as 10 seconds, your step time as 10 seconds, and the rest of the properties, you can keep it the same. Just your maximum temperature change per unit needs to be changed to 1 Kelvin degree. So once you're done with these changes, you can just press on OK, and we have a step setup too. So I'll hold on a bit, and the ones who are trying to replicate it, you can do it. If there are any doubts or anything, or if you want me to repeat, you can let me know. I'll do those steps too. Okay, so I hope most of you were able to do it now. So now we'll go and create our initial thermal conditions. But since we are doing a transient heat transfer analysis, we'll need to define an initial temperature for the component 2. So we'll select initial temperature, and the initial temperature will be applied to the whole model. So you can select if there's any particular ones that you want it for, but we are going to apply it for the whole model. And we are going to initialize this model to 300 or Kelvin degree. Okay, so as you also read that you could map a given partial data to, so you can map the data or you can just press equal to and so for partial data you'll have to give in table input. But in our case, we are just trying to give an initial basic condition of 300 Kelvin. Okay, so this option you will find from your initial conditions and initial temperature. So once you do that, you can just press on OK, and your initial condition will be created in your scenario. The next thing which you'll have to define is the thermal conditions. Yeah. So you can just go into thermal, and there is a film condition. So film condition is what we are going to apply. It's basically the heat transfer between a part and its surroundings. So we'll just apply a film condition here. And the surface which we are going to select is the cell surface. You can select as I selected on my screen. You can just from the geometry itself, you can select it. This is how the surface needs. This surface is the one which we are applying the film condition. So just make sure you select it. The values that we have to give an input for the film condition are 16 watt per Kelvin degree, and the reference temperature is 500 Kelvin. So you have to select the face of the cell, and the values which you have to give in for film coefficient are 16 and reference temperature is 500 Kelvin degree. So I'll hold on a bit for the ones who are doing it, and then we can proceed with the further steps. So for the ones who have done this step, you can just click on OK. And now what we have to do is we have to establish a contact here. So like I said, you have this contact properties. So we go into interaction and we'll select contact properties. The contact property already has an input here, which is the conductance is 1 plus 6, 1 e power 6, and then we have the clearance which is defined. So we do not need to make any changes with it, but in order for us to create a contact, we need the contact property present. And if there's radiation that is occurring, then we can specify the radiation emissivity data if we have those emission, if we have radiation type of an heat transfer occurring. So in our case, we'll just do OK for conduction. And now that we see our conduction property has been created, so we need only one conduction property, and then we'll be defining a surface or contact between them. So to define a contact, what you'll have to do is you can just go into surface-based contact. And the way we define the contact is between so we'll have to select a main and a secondary component. So I'll just quickly show you how to do that. So the main component is going to be our cell, and the secondary contact is going to be our insulation cap. So what we can do right now to select the cell, since the insulation cap is covering the cell, is from the specification tree, we can hide the mesh for the insulation cap. So that is mesh 2. We can just right click on it and hide it. And similarly, we'll do it for the geometry too, which is, and this is the surface which we need to select as the main surface. So we'll just select this surface. So you just need to hide your mesh for the component and for the component itself. And for secondary, the secondary is going to be the bottom surface of the insulation cell. So we'll just again show it, and this time we'll hide a cell. And you can just select for secondary, just make sure you have the selection done for the secondary before you select the component. And you can just click on secondary here, this particular bottom surface. And the contact property which we have, the one which we created is contact property 1, and it's already been defined here. And you can click on OK. So I'll replicate this step again, but yeah. So this is how you define a surface-based contact. So you need to select your main surface and your secondary surface. So I'll just replay the process again. So go on to surface-based contact. There are two types of contacts which are here, main and secondary. The main one is the top part of the cell. Now, since there is an insulation cap present, we cannot directly select the surface. And since they are in contact with each other, we are not able to select it directly as well. So for that, what we do is we go and hide the secondary, the insulation cap component. And we go and select the main surface as this. Now, since we have selected the main surface, we'll just click on secondary. We'll unhide our insulation cap. And we'll hide our cell right now. Since the secondary surface is going to be the one which is the below one here. And once you do this, you have your second surface-based contact also ready. So this is how it is done. I'm not creating it again since I have already one created. But that's how you do the process of creating the contact here. So now you can see that in the assistant, we have everything created from setup to paths to interaction, the thermal conditions, everything is defined. All you need to do now is to simulate the model. So we'll just quickly update it once to see if there's anything that we have left out. And now that you can see there's no error or warning that has appeared, and all the components are updated, we can go on to simulate, and yeah, we can hit simulate right now. So we'll just let it simulate right now. We'll click OK. So the model might take about 2 to 3 minutes for it to simulate, so we'll let it simulate. In the meantime, if anybody has any doubts, they can ask us about it. Okay. Okay, the composite domain, right? Okay. Simulation is running. I won't be able to show it to you. Let's see if it's on. Okay, I'll show you what a composite. Okay, I think I'll be able to access it from here. So, like somebody had a doubt in regards to what does composite domain mean. So what you can do is you can just search composite domain here. And once you press enter, you'll be able to see what exactly the composite domain means to. So adding a composite domain. Yeah. So you can add a composite domain, either double click, or this is just a procedure to add it. The section properties are defined for composite parameters. Okay, I haven't used that command yet. Oh yeah, Herschel, I haven't used the command of composite domains yet, but you can explore it, and maybe on the courses you will have an option of what these composite domains do actually. So we'll just see if our model has simulated or not. Okay, the simulation has done. Okay. So we'll just close our resistance box and the temperature. Right now, if you can see, if I play the animation here, I'll just slow it down a little bit. So if you can see the temperature change that happens in the fluid in the given component, it's AWaDH should do. Yeah. So this is how you'll be using the thermal option here. This is the temperature plot. Then we also have the heat flux plot. So heat flux will be a vector plot of how the temperature is changing and how the flow of the temperature is occurring in the given component. Then you could also see the changes in the model as to if there's any physically structural changes that happen in the model with the application which we have done here. So you can also see the maximum and the minimum heat flux properties, where they are present and what are the properties for them. And on the similar lines, for the temperature, you can do the same. You can just go select the maximum and minimum temperature. So you can see the maximum temperature is occurring at about this step, and the minimum is on the top part. So this is how we'll be generating a simulation in terms of a thermal component, and the analysis could be anything. You could either, so on the similar lines, you could do it for a whole battery pack itself. So I'll quickly show you a video which I have done on a battery pack which we have. So this is a simulation for a complete battery pack wherein you have the connectors, then we'll also be placing with the cells which are in series, the cells which are in parallel, and then you can establish the whole the heat flux and the temperature plots for them, and you can see how the battery pack reacts and how the temperature fluctuation happens in the battery pack itself. So the details of the fidelity models could be from, you could just have a whole battery pack simulation done to from a cell model. So there's a lot you can do on the Simulia applications itself on the thermal side. Yep, so if there are any doubts or anything, you can put it on the chat box, or you can unmute yourself and ask us about those doubts too. Okay, so could I have a head count as to how many people have actually been able to do the simulation? If you have, you could just put your yes or no on the chat box so that if there's anybody who needs help, I can help you with that. Okay. Praneeth, could you share us your screen? We can have a look at your screen and then try to fix the error.
Think I'm the option is not available.
Okay, I'll just make you as a presenter and then you'll be able to present your screen. Yeah, I've made you the presenter. Just check now. You might have the option available now.
Yes, also it's available.
Yeah, could you just share us your screen? We'll just take a look at what issues you're facing.
Is my screen visible?
Not yet. It's loading. Might take a while. Let's wait. Okay, I'm not able to see it. Is anybody else able to see it? Okay, now I'm able to see your screen. Yeah.
This is the error I got. Wrong. I mean, I think it's mistake with my contact.
Okay. Could you unhide your components once? Just go on to tetrahedral mesh and unhide it. Right click on it and you can unhide it. Yeah, just right click on the component and you'll be able to unhide it too.
I mean, it's taking a time. Yeah.
Okay. Well, similarly for this one. Okay. And could you just expand your specification tree a little and go into your scenario component?
Yes.
Yeah.
This one.
Yeah, the thermal analysis step, just maximize it. Okay, so there is an interaction option, right? Just go into interaction, yeah, and maximize that. Yeah, so you have about a few, okay, so there's a lot more surface-based contacts that have been created. Okay, so could you delete all of them from 1 to 4? Just leave the first one there and delete the, so there's the last option is delete. Yeah, just leave the fourth one, let's see. Just double click on the fourth component. Okay, zoom on to your tree once, or the components. Okay, so both have one face, right? Okay, just cancel it and try to simulate the model again.
Yes.
You have this generator. Yeah, we'll wait for the model to simulate, and I think it should simulate now.
I think it's similar.
I think it was mainly because you had created a lot more contact properties, and that's why the error was there.
Yeah. So I mean, I try to create more contact.
Right.
Yeah, it's just yeah. Thank you.
No problem. We'll just wait and see how the simulation looks like, and then we'll see if somebody else has it out, and then we can do that. Yeah, I think it is simulating. Okay, you can stop presenting. I think the model will simulate now. Once you have it. Is there anybody else who has any doubts, anything that they want me to answer about? So I can help you with that part too. Okay, since I don't think anybody else has any doubts, what we can do maybe is, or okay. Yeah, Lloyd, sir, are you there on the call, or there, Dr. Dheeraj?
Yes, Siddharth, tell me.
Yeah, I mean, since we have done with the thermal simulation, do we take a break for lunch and then start with 1D simulation after that?
How much time would you need for 1D simulation, Siddharth?
I think I'll be needing about an hour, like about 1.5 hours or 1 hour. That's it. I mean, we'll be running through two examples and then we'll be understanding what exactly Daimola is as a tool.
I think we will ask Dr. Dheeraj. If Dr.
Yeah.
Dheeraj is not there, do we have Dharmender?
Yes.
Dharmender, can we break for lunch and continue the session
Yes.
later?
Yes.
Because Siddharth,
Yes. Sure. We can break for a lunch and then we will start again.
so we can start at 2 o'clock or 2:15. What time is it?
I think at 2:30.
2:30 is good.
2:30 is good.
Sure.
Then,
We can
Siddharth, then
connect
we
back
we
to
break
two
for
continue
thirty.
lunch.
at
We can
2:30.
start at 2:30.
Yes, sir.
Sure. If anybody has any doubts in the meantime, they can post it on the swim communities or on the chat box and we'll be happy to answer your doubts.
If anyone have any doubt, then he can continue at 2:30. Also can interact with you. So let's have a break for lunch at 2:30. We will meet again at 2:30.
Thank you all of you. We'll connect after the break.